Angerhausen with SOFIA.
Yeah, good morning. I'm Daniel, and I guess I've won the size competition because my instrument today is the size of a plate. But before I start talking about SOFIA, I want to do some quick announcements and acknowledgements. For example, 3 other emerging young scientists from the field that can't be here today. One is Emdelam, who was my undergrad student at FPI. She's at UCF with Joe Harrington now, and she did some really nice work on Kepler eclipses. Then there's Ben Plachek from SUNY Albany, who wrote really nice Asian phase curve modeling code called ExoNest. And then there's Brad Morris from the University of Washington, who I work with on Moss Fire, which is similar to the GMOS observations we heard about yesterday, but in the infrared. Also, I'm co-organizer of a conference in Nice, France this October, so if you're interested in exoplanet atmospheres and habitability, maybe check that out and come to France this fall. And last but not least, Mark Kushner from Goddard asked me to advertise that he has a grad student and postdoc position, so if you're interested in, he's mostly working on disks, so if you're in this field and looking for something, hit me up or talk to Mark. Okay, so quick refresh of your knowledge about spectrophotometry. We had a couple of talks about it yesterday. So for some systems we are lucky enough to look edge-on, and then most of the times we get these primary transits or secondary eclipse, and from the difference before-after or from measuring these transit light curves, we can actually not just detect but also characterize the planets. And what you usually get are these transit light curves. In this case, optical light curves from the red to almost to the UV, and obviously it's nicer to have more data points and more wavelengths than just one broadband, and this is why we call it spectrophotometry. So you can either come from multi-imagers, so take 5, 6 different imaging bands, or you take a spectroscopic instrument and bin down your resolution to certain wavelength bins, and then each light curve in these wavelength bands represents a spectral value at that particular wavelength, and then you ask your colleagues to fit the models to that data, and then you find out in this case, for example, that there's water, methane, and CO2 in the atmosphere. And of course, you all know that it's way more complicated, each of these steps, but that's just a 30-second expert for spectrophotometry. And what we can do right now, with the technology we have right now and the methods we have right now, is mostly our Jupyter work. So we can check on the atmospheric composition, we can do the atmospheric structure, like temperature, pressure profiles. You can also draw conclusions about formation history, and one big question that we are just starting to answer and might be able in the next 5 to 10 years is that whole super Earth versus mini Neptune question. And hopefully, sometime in the not so far future, we might also be able to look for biomarkers using the transit spectrophotometry method. Okay, so let's talk about SOFIA. Yeah, okay, so SOFIA is a telescope on a plane, and it's a 2.5-meter telescope carried on a Boeing 747 SP. It's a joint project of NASA and the German space agency DLR. It usually observes at altitudes about 40,000 feet, so slightly higher than commercial airplanes. The first generation of instruments are 7 images or spectrographs from the optical to the very far infrared, and basically the main purpose of SOFIA is the longer wavelength, so it's kind of like a Herschel kind of science case mostly. It's supposed to operate for 20 years with about 120 nights per year, so not every night like a ground-based telescope, unfortunately. A couple of milestones. So in April 2007 we had the first test flight of the observatory, which is tricky enough to have that huge mass in the back. Instead of just evenly distributed people, you have that huge 16-ton telescope in the back. Then in December 2009 we had the first open door flight, and that's actually what we see in this video right now. And that was actually the only time that they opened it during the day, because it's a huge, obviously a huge danger to fly with an open telescope on a plane. And if you look in the sun, suddenly the plane burns, so you don't know. And then actually I just see that it's almost to the day 5 years ago that we had the first light observation with SOFIA, so it's already quite some time since that. And then since 2011 we have actual science operations, so we are right now in cycle 3, so the actual call for proposal just came out, so you can propose for cycle 4 now, I think, or you can propose for cycle 3 now. And a couple of the advantages for transit observations: we are obviously working in the right wavelength regime, as we heard before. All that funky photochemistry, a radio split in, is mostly happening in the optical and the infrared. It's a mobile platform, so for those of you who observe transits know how tricky it is sometimes to schedule a transit on a ground-based telescope, and sometimes you only have like one night and then it's raining, it doesn't work. So obviously you can use SOFIA because it's mobile, at least theoretically, to go to the best place in the world to observe that one transit that's happening. Then the main reason why SOFIA was built is obviously less atmosphere, so you're flying up above more than 99.9% of the atmospheric water. And especially for our time series observations, it's not really the absolute absorption of the atmosphere, but the dynamic changes on time scales that are similar to the transit, so we get less of that. And one of the most important things is that SOFIA, I always call it a space telescope that comes home every morning, so you can put on the newest instrumentation, at least again theoretically. So, and we talked about that yesterday briefly. I think it's time to have a dedicated transit instrument, and maybe SOFIA might or might not be the platform for it. And as you can see here, in 2011, part of my PhD thesis was to think about all these theoretical advantages of SOFIA and build on that science case. And actually this week I got the first observation accepted, the paper for it. So that's an example how in your career you sometimes have to be really patient and persistent to finally finish up such a project. And just to illustrate that whole SOFIA getting there. So one example, for example, I got an observation. So I've met SOFIA. I met SOFIA a couple of times in the hangar, so I was there very often. Submitted a proposal, got time accepted, flew actually during my vacation in Germany, flew to California to do a transit observation with SOFIA, and the day before we started, a small fuse burned and we couldn't start. So actually they ordered this fuse on eBay the next day for $10, with $10 spare part kept the $1 billion plane. And since there's like the big phone book size procedure, stuff like that happened, it took 6 weeks to bring it in the air again. So this was the first time I was supposed to fly, but then finally in 6 months later I got another chance, and then finally did my flight with SOFIA. So it really takes sometimes persistence and patience, and if it doesn't work one time, I mean, I guess all of the observers know that, you get that one proposal accepted and then it's raining in the Atacama Desert or stuff like that. So just, stay with it. Eventually you're going to get your night. And so then, finally on October 1st, 2013, we got our first Exoplanet observation with HIPO, which is the combined instrument of FLITECAM in the optical, in the infrared, and HIPO in the optical, and we observed the transit of HE 1897333b. And this is the first light curve we get, and this is absolute photometry. So we don't have a comparison star, so this is basically space-based quality because you don't need a comparison star anymore. And all of you people who do transit light curves maybe can appreciate how cool that is, that you don't really have to compare, so you can really, especially for bright targets like HE 189, you can take full advantage of that. And this is the result of that observation as it was just accepted. So in comparison to some Hubble and Spitzer observations, we are right now at 1.5 times the photon noise and get a precision of 185 and 160 ppm in these two channels. And if you take into account that it was a really first observation and we still have to learn things and we just had very little baseline, I think we at least play somehow in close to the league of HST and Spitzer as a platform. I'm not sure if the instruments really can do that long term, but at least we can compare to these platforms. Then another observation that I'm working on right now is GJ1214b that we heard about yesterday too. And there we got 4 channels at the same time, 2 or 3 optical channels, one actually with the guiding camera, and one really narrow, infrared band, which is quickly speaking through that. So here you see the bands that we can observe with SOFIA on FLITECAM, which are exactly between H and J and K and L. So these bands that are completely opaque from the ground, we can choose really narrow filters to observe these. You can see these black other observations. We can refill the gaps between the other observations. And since I'm running out of time, I'm skipping through this and just want to argue that before James Webb starts, and even if James Webb is flying, we need alternatives. And as you mentioned yesterday, I think either SOFIA or ground-based telescopes need dedicated instrumentation. And actually, since the x-axis is a little bit off, because the old side, I correct for that. And while I'm answering questions, I'm showing this video of a SOFIA observation in Palmdale, and I hope you're not too much distracted and have time for questions. Thank you.
Two questions.
Mm-hmm.
How well can you guide?
Guide or point?
Either way.
Okay.
Point and guide.
Okay, so the pointing stability is about 1 arc second. So 1.5, 1 arc second, that's the pointing stability that you can get. So people always compare, I don't like these comparisons, but some people say it's like riding a horse and aiming with a gun and a dime in 50 meters. I'm not sure how that compares. It's tricky, but it works.
So what is the PSF size, the forward half mass of your PSF, compared to your guiding?
I don't really know that out of my head actually. It's slightly ellipsoidal actually, because in the optical we get like a shear layer in front of so you get like pressure differences that kind of elongate the PSF. But off my head, I don't really know the fullest of marks on that.
And is there a target of opportunity mode, like is there a trigger mode if you have a target?
In principle, yes. So there's TOO and DDT time as for every other observatory. Right now it's a little bit tricky since the policy is to start and land in Palmdale, and SOFIA's door just opens to one side, so you can fly, let's say you fly eastwards, you can observe to the south, and then after 4 hours you have to turn around, you can only observe in the north. So the maximum time right now on one target is 4 to 5 hours, which is actually kind of a problem for transit observations, because some transits are longer, or you want to have lots of baseline before and after. But in principle, it's possible. So fly up to 10 hours on one target. Yeah.
For those of us who fly commercial aircraft, it's amazing that you can do astronomy from the air. I'm just wondering, do you get up to a point and then measure the stability of the atmosphere at that point, and then either adjust your trajectory or cancel an observation based on the stability of the air that you're flying through?
I mean, you definitely have to watch the weather. Obviously, like normal planes, if there's like bad weather, we have to go around it. But as soon as we are flying, actually the telescope takes over the plane. So the telescope is completely steering the autopilot, so the pilots take off their hands and the telescope takes the plane. Yeah, these guys have an easy job. They just have to start and land, and then copy the rest of the time. So, I mean, we definitely get lots of housekeeping data. So we observe the Mach number, the air pressure at the altitudes, the temperatures, just to decorrelate our data with it. So we get tons of that data, but I don't think there's any. I mean, unless there's like super large turbulence and stuff, that there are any triggers that we have to stop for some outside reasons. If that answers your question.
Yeah. So Boeing aircraft 747 is over 20 years will be kind of expensive for fuel to maintain. So what's the advantage of using a 747 over maybe a lighter aircraft?
I mean, I totally agree with the price. SOFIA is really expensive. The thing for the SP version was that it was basically free at that time. So it's the 747 SP, I'm not sure, I mean, probably only the aircraft experts know it, but it was a shorter version that was built to fly directly from California to Japan, I think, without stopping in Hawaii with this like engines that were not that good, but then the engines got better and you could take the full version, and then all these Boeing 747 SPs were just like, nobody needs them anymore. So that's why they used the 747. And as usual for these projects, SOFIA is like 20, it's like in the planning for 20 years, and that was just like the biggest plane available at that time. They want to fix the big telescope. Oh, this is also interesting. So you see the telescope moving, but it's actually not the telescope moving, but the plane moving around the telescope. So the telescope stays completely straight on target, obviously 1 arcsecond precision, and you only see the plane moving around the telescope. So.
Do you have to defocus at all, or do you have enough pixels over
That's stuff that we are still trying to figure out. I mean, people who do transit observations know you always want to tweak a little bit the focus, but don't want to really go to donut land. So that's still things we are trying to figure out. But usually we defocus a little bit, just also to account for not to be too dependent on the flash fields, for example. So yeah.
Is there any plan to add new instrument on SOFIA, and how hard it is to apply, say, to modify the current instrument or add parts of the
So there are actually reoccurring calls for instruments. So there was just one in this spring, like a call for 2nd and 3rd generation instrumentation for SOFIA. So, and we actually had for the first call of instrumentation, we had a multi-channel imager Exoplanet instrument put in, but that wasn't really. People thought it does the same that James Webb does, so it was rejected because of that. But again, you know, we did dedicated transit instrument, not just James Webb. So, yeah. Oh, but there's a call for proposal. If you have an idea for an instrument, there's supposed to be a new instrument every year, every 2 years on board. There's also money for it somewhere, which is probably the most important question.
All right, let's thank him again.